Good morning or good afternoon, good evening, depending on where you're joining us from. Welcome to the Hurry Institute for Computing here at Boston University, where we're bringing to you our panel discussion to close up the Machine Learning for Model-Rich Problems speaker series that we've been hosting. So the Hurry Institute is BU's primary institute around computing, the focus on converging computing and transforming. We lead dedicated and integrated initiatives aimed at research and technology development, particularly targeting disciplines at the nexus of computational sciences. We've got core strengths around a variety of areas, including AI, cyber, cloud, and many other areas. So if you've been fortunate enough to be able to join us, you've seen in this series that we've talked about machine learning as a powerful paradigm emerging from CS and statistics, found effective in applications across all kinds of different disciplines. And we've been featuring 4 leading innovators working at the interface of machine learning and theory-driven modeling from the domains of astrophysics, biophysics, econ, and structural design. And now they're here to speak together about how to incorporate the benefits of data-driven modeling and machine learning into their disciplines. I think what struck me particularly was the variety of model-rich domains that were embracing machine learning. So I was just reassuring the speakers here that it's okay that they're not all from one particular discipline, as we're usually used to in our workshops and conferences. We're actually looking for them to embrace the fact that they're from different areas, but they're doing things that are very similar in many ways. The different ways that theory and data can be integrated to inform solutions was also really fascinating to see during the talk. Some folks are bringing it to bear formally in the sense of bringing PDEs as part of the modeling they were doing. Other folks are using PDEs to constrain what the machine learning was doing. The extent to which modern machine learning software workflows are being used to facilitate this work is also really fascinating. Some folks have been developing their methodologies and the computing from the ground up. Other folks have been tapping into workflows like TensorFlow, for example. So there's just a fascinating array of options and possibilities we've seen here. And at the end of the day, the sheer breadth of impact derived from this approach really seems like something that's just only beginning to be tapped. So I'm going to finish up this brief intro, and then I'm going to turn it over to the 2 hosts that are our junior faculty fellows. If you have questions, we have a handful of questions that we've put together ourselves to kind of guide this, but we have plenty of time as well for a Q&A from the audience in the last third of this panel series. So if you have questions, please enter them into the Q&A feature, and the panelist hosts will be actively curating those and pulling them together to guide the Q&A for the rest of the session. So let me introduce our 2 moderators, and you've seen them already if you've joined us earlier in this series, right? So we have Emma Lejeune and Alison Segros. I'd also like to thank the other 2 faculty who helped with this series. This was Wen Li, who's an assistant professor in astronomy, and Andre Fragkin, who's an assistant professor in marketing in the Questrom School of Business here. So quick intro about Alison and Emma. So Alison is assistant professor in biomedical engineering and a junior faculty fellow in Hariri. She started out on the East Coast, attended Simon's Rock College, and then moved on to University of Washington, Seattle for her doctoral work. Right. She is currently a assistant professor of biomed engineering, as I mentioned, but also a member of the Biological Design Center here at BU. She became a Moorman Simon Interdisciplinary Career Development Professor recently and holds a joint programmatic appointment with physics. And then Emma is an assistant professor of mechanical engineering at BU. Her background is the area of computational mechanics and computational biomechanics, where she works to leverage state-of-the-art in computational mechanics to investigate multi-scale emergent behavior in biological systems. Her current areas of research involve integrating data-driven and physics-based computational models and predicting the mechanical behavior of highly heterogeneous soft tissue. So I'm going to turn it over to them to introduce our panelists and to take you through the rest of today's panel.
Fantastic. Thanks so much, Eric. So our first panelist is Celia Kamendi. She's professor of physics at Freie University in Berlin. She joined their faculty last June after 19 years at Rice. Before then, she had obtained her PhD in Italy and then was a postdoctoral fellow at the University of California in San Diego. Her research focuses on developing machine learning methods to understand biophysical processes, integrating molecular dynamics and system mechanics together to understand biomolecules. She's earned an NSF Career Award, as well as the Robert A. Welch Foundation Norman Hackerman Award for Chemical Research. And she's co-director of the National Science Foundation Molecular Sciences Software Institute.
Yeah. And then Miguel Besa, another one of our panelists, is an associate professor in the Material Science and Engineering Department at Delft University of Technology and the director of an interfaculty AI lab called Machina. He was awarded the prestigious Venny Personal Grant in 2019 from the Netherlands Organization for Scientific Research. He received his PhD in mechanical engineering from Northwestern University as a Fulbright scholar and was a postdoctoral scholar in aerospace at the California Institute of Technology. His research involves understanding and modeling materials at different scales in a new experimentally validated and self-consistent computational framework. And he envisions a new era of design of materials and structures through machine learning.
Joshua Blumenstock, an associate professor at Berkeley in the School of Information, director of the Data Intensive Development Lab, and the faculty co-director of the Center for Effective Global Action. His work focuses on how machine learning and empirical economics work together, using new methods to better understand how causes and consequences lead to global poverty. His PhD work was in information science from Berkeley, and he also has bachelor's degrees in computer science and physics from Wesleyan. He's also earned the National Science Foundation's Career Award, the Intel Faculty Early Career Award, Gates Millennium Grand Challenge Award, Google Faculty Scholar Research Award, and the UC Berkeley Chancellor's Public Service.
And Jacob Bortnick is a professor of space physics in the Department of Atmospheric and Oceanic Science at the University of California, Los Angeles. He is interested in a variety of topics that include lightning-generated plasma waves that whistle, the belt of ultra-relativistic electrons that encircle the Earth, making waves in laboratory plasmas, and most recently in the applications of machine learning techniques to squeeze knowledge out of data. Thank you all four of you for joining us today.
Thank you.
All right, just to get the panel started, one of the first questions that was prompted by your talks was that in all of your fields, it looks like theory-driven modeling has a long and established history, while its integration with data-driven modeling and using machine learning is relatively new. What sort of acceptance versus pushback have you found to your work in your fields? If you don't want to chime in, I'll also go ahead and call on people. But I'll do the uncomfortable silence.
I can start if you want.
So
there has been a lot of resistance in my field, especially from the old school theoretical physicist or theoretical chemist. They, some of them consider machine learning some sort of voodoo, like you mix things together, something comes out. But I disagree, because I think that you need to use theory, you need to use physics and chemistry and the knowledge we have. I mean, it's not that easy. Machine learning is replacing what we used before. It's an addition to what we used before. It's a new tool that we can integrate with what the theory we used before to go beyond. So I don't see it like some magic that replaces the traditional way of doing science. It's a new tool in our toolbox.
I can jump in. I mean, I would echo those sentiments. So thinking about economics as a discipline, I would say it's not a discipline that has historically been known for its openness to outside methodologies. And so I think as a field, economics didn't jump to embrace the methods and approaches of machine learning. Historically, economics has been very concerned with questions of causal inference, which requires some very rigorous notion of a counterfactual, like what would have happened in the absence of something that did happen. But I think more recently, and I mean really recently, over the last few years, people have gotten excited about some of the intersections between machine learning and economics. I guess like two immediately jump to mind, two areas of work. One is about sort of this intersection between the like statistical machine learning and econometrics. In other words, thinking about how insights from machine learning can be used to improve our ability to conduct causal inference, thinking about methods for estimating heterogeneous treatment effects or those sort of approaches. Another area is what economist Sendhil Mullainathan has dubbed prediction policy problems, which is, a lot of economics is very adjacent to public policy, and the recognition that a lot of times the correct policy prescriptions really require some are prediction problems fundamentally, like understanding what policies are best for specific segments of the population, or what types of interventions would be best to improve outcomes in a subset of the population. And there's been a more recent recognition that this is exactly what a lot of the tools of machine learning are really optimized for. And so I think there's a lot, even though, to echo Celia's point, this isn't an area where like all of the old school economists jumped on the bandwagon at day one. I think there's a lot more excitement now.
If I can add something, I think the way eventually machine learning will be accepted is by means of, we can convince people by demonstrating it with our work. If we show, at least in my field, if we show that we can get results, if we show that we can go to where we couldn't go before, then is going to be an evidence that is going to play in the favor of using machine learning.
Yeah, I don't have much to add, but I think in the mechanics community, there was one challenge, at least that I think the community identified, which was related to the quantities of data. So I have the impression that, for example, in economics or computer science, there's more open data sets, even though perhaps not as well organized as computer science, perhaps in economics. Joshua, you can correct me if I'm wrong, but in mechanics, it's a very closed field. So oftentimes people analyze the materials, for example, to describe the mechanical behavior in their own labs. The data is not shared. And an additional difficulty is that even if you do simulations to predict the behavior of these materials and then use that data in the machine learning models to get this behavior, if you do that for elasticity simulations, they're very fast and you can create enough data to use these methods. But those models, the analytical models, are already actually quite good in most settings for that particular class of problems. So for a long time, people didn't see a need for machine learning really in this field. And if you go to the hard problems, and it's not just about solids, turbulence and flows or something like that, these simulations are extremely expensive and you quickly get into the data scarce regime as well. So it's kind of you're stuck in between a problem where you have a lot of data, but maybe you don't need it really to come up with a new model, or you don't have enough data because the simulations are complex and time consuming. And these models, then there's a few exceptions, but in general, machine learning really shines when you have, enough data, and that changes from the problem, of course. So our entry point was to actually create a reduced error model and bring attention to, if you speed up the simulations, you have enough data, and then you can bring these to the field. And recently, like both of you were saying before, you see a shift. So a lot of people now are looking into it, and all these different aspects are being addressed, which is really cool, I think.
Jacob, you look like you had some thoughts on space physics. Go for it.
Yeah, I think I'll just support what Cecilia, Joshua, and Miguel said. I pretty much have had exactly the same experience. There's kind of an older school of folks they understand the theory, they're used to science being done a particular way, and introducing this kind of shiny, big tool that gets a lot of hype is a little bit maybe intimidating or scary, or they don't quite understand what it is. Some folks who have a vague idea just might think that it's just function fitting. And so what's new about that? And other folks that I've heard criticize machine learning would say, well, I haven't seen machine learning produce anything new, which of course, at the beginning of any new technology, you don't see anything new being produced when it's new, but you wait some time until people figure out how to properly apply it and how to use your new tool in an effective way. Some of it, I will say, is also on us, the practitioners of machine learning. And I've been a reviewer on papers where people have used incredibly sophisticated deep learning techniques to just kind of, if you just draw a threshold in your data and some signals poke out, you could probably do just about as well as your big fancy deep learning models. So I've seen people kind of abuse this new tool to do things that are very simple and could be done in a much simpler way. So for us machine learning practitioners, I would say just be judicious in what you actually use machine learning for, because you can give the impression that it's just a very shiny, fancy new tool that does nothing new. It doesn't add anything above what's already being done. With that said, I would say that my former panelists have said it exactly right, is that there is tremendous potential, and it's kind of on us to really show where the delta is. Like, where does machine learning go beyond what can be done in the traditional ways? There's no replacing fundamental theory, and that's not what machine learning is designed to do. It's just a tool to point you to areas that you just couldn't spot with your regular, looking at time series from some experiment or something like that. And machine learning can summarize and compact a lot of data, a lot of high dimensional data, in ways that are easy for us to kind of see what's going on. Perhaps kind of challenge our intuition based on theory.
Yeah, and that actually, I feel, almost segues into the next question a little bit. So in a lot of the examples touched upon during the talks, where data-driven modeling is interfacing with these model-rich fields, data-driven modeling is primarily used to augment the theory-driven modeling. And I guess my question for everyone is, do you anticipate that aspects of theory will either evolve or be entirely reformulated as a direct result of these data-driven modeling endeavors? Or do you think that's not necessarily the direction that things are going in your fields? I know Jacob actually touched on this a little bit in his talk, if I recall correctly. Even though he just spoke, maybe that would be the first person to go ahead if you're comfortable with it.
Sure, we'll just ensure some kind of a symmetry, first to last, last to first.
Yeah.
Yeah, so in terms of fundamental basic theory, I don't know that we'll be discovering anything completely fundamental. But in terms of the way we model our systems, we use this the Fokker-Planck approach to model our radiation belt system using a diffusive framework. And even just seeing what the state of the art simulations do, it is clear that at some points they're just not getting it right, because the model sometimes acts non-diffusively. But people just they love this framework, they understand it, they just want to beat our system into obeying this particular equation. And I think that where the power of machine learning, or for example PDE discovery, is going to shine is it's going to say at sometimes during the lifetime of your system, new terms are going to arise. And so there you go, scientists, tell me what these new terms represent. And I think that's going to be exciting, because it's going to give us insight that somehow, like, stubbornly, we don't want to go there. But the machine learning is going to say, well, that is what your system is showing you. And I think this is kind of the flavor of where machine learning is going to change things a lot in my field. Kind of pointing to effects and putting in new terms into equations that you somehow stubbornly don't want to put in there, but they do belong in there for a complete description of the system.
Yeah, thank you. Yeah, maybe we'll maintain the symmetry, and Miguel can pick up on this idea of using machine learning to point to new terms that should really be there, or take it in a different direction. Up to you.
Sure. happy to. So there's a group close to Boston at Brown University by George Karniadakis, who basically leveraged the work from, I think, Kennedy and O'Hagan in 2000s, where they used multi-fidelity machine learning techniques to mix different models. And at the time it was mixing different simulation data, different fidelities for the data, very high quality data and low data that you can collect for in large amounts. But this could also be extended to having an analytical model or any kind of model that is already established with years of research, and mixing it with additional data that complements, just like Jacob was saying, that complements these well-founded models that are there, and they are largely predictive, at least most of the trends. And where they're not, and where we have failed to find a theory that explains it, these tools can augment it and basically complement that and provide useful information for to move forward, I think.
Yeah, thank you. I don't know, Josh, is it similar in economics, or is it a totally different world?
I mean, it's a different world, but it's a similar theme. I mean, I think I'll make 2 points. I think one is that one, I would say, very low-hanging fruit for how machine learning can contribute to economic theory is sort of by allowing economists to observe what has historically been very difficult to observe. This is almost like machine learning for measurement. But I mean, an example is from the work I talked about myself, right? Like a lot of the field of development economics is about understanding causes and consequences of poverty. But surprise, surprise, poverty is actually very difficult to measure, particularly in low and middle income countries where people don't have traditional forms of income that they report to the government. And there's been a lot of work in the last 5 or so years showing how high resolution satellite imagery, how data from financial networks and mobile phone networks can be used to estimate welfare at a very granular level. That in turn enables approaches to understanding what impacts welfare, because now you can observe welfare in a way that was previously much more difficult. And so this sort of like iterative process between measurement and testing of theory and redevelopment of theory, I think, is something that machine learning can contribute to. One other quick point is I think there's also like a lot of room on the flip side for economics as a discipline to contribute to the theory of machine learning, right? Like a lot of like probably 95%, 98% of machine learning algorithms out there are optimized on some objective criteria like error rate or accuracy or AUC or, you know, some derivative of performance. But I think one thing that economics can contribute is a much broader notion of what optimization means, right? Like what is a societally optimal outcome? And to think about how machine learning optimization routines can be a little bit more broadly defined, so as not to just like replicate a label on a training observation, but to actually try and produce some synthetic, holistic outcome that is, you know, conforms to a theory-driven notion of what is optimal.
That's really interesting. Cecilia, do you have anything to add as a final point on this question?
I agree with what has been said. I think so far we have seen the low-hanging fruit. What was easier to do, that is in my field, instead of guessing a functional form for an energy function or some complicated function we don't have an idea, we use a neural network or some other sort of function approximation. That's the easy part. I mean, we can apply this model over and over and over in many different areas. But the difficult part is what I'm mostly interested in, and I think we'll see in the future, is that machine learning, as has been said, can help us discover things we haven't seen in the data before. We can see new phenomena that we can help us distinguish between noise and the signal. And the signal may be related to physical processes we ignored before. And now we need to think, we need to go back into the theory and intuition and interpret this signal. So this is what I think is going to happen, and I find it very exciting.
Can I just jump into something Joshua said for a minute? I think touching on the notion of complexity in your optimization, I think this is something that is really important because in simple machine learning algorithms, you have kind of a mean squared error, or you have, some goodness of fit to some very simple criterion. It's a cost function. You try and squeeze down your cost function by tuning all the free parameters in your model. But we as humans, we work in a much more complex way. When we make decisions, there's this factor to consider, and that factor, and that factor, and that factor. And I think to become reasonable and to become a valuable, not tool, but almost like an advisor, I think this idea of a cost function that's complex and represents values and different trade-offs, I think it's really worth a lot of thought. And I really like that Joshua touched on it. In the physical sciences, we touch on it by minimizing not only your mean squared error, but let's say you have a physical law or a conserved quantity. You can say, conserve this too, conserve that thing as well. And how about when we look at data, we as scientists are like, this is reasonable and that's unreasonable. How do you know that? And how do you tell the machine to say, think of things that are reasonable, or even go a step further, look for things that are reasonable and tell me what stands out to you in the data compared to that. I think this area it's subtle, but I think this is where a lot of the value lies too.
Thanks so much for that. So one of the words that keeps coming up is data, right? Much of machine learning, particularly deep learning, requires large amounts of data. But it has to be a certain kind of data, right? If there's limitations in the data or problems in the data or not a certain kind of data available, that can potentially be a challenge for you. Has this been a challenge for any of you in your own work? And if so, what do you think is going to change in your field that will make the right amount or kind or type of data available? What are you seeing just off the horizon in that regard?
In my field, there are a lot of shared repositories that are being created. So we see a lot of databases, and people more and more are, when we publish a paper, are requested to share the data. And then there are efforts to pull the data together. It's a problem because the data may not be completely consistent if they're generated on different systems by different people. So I think as a community, we are going toward the direction of trying to organize ourselves to produce data in a way that are reusable and of value to others. So they can be, maybe if they can be, the data can be published and cited, there is going to be an incentive to generate better data, or to make to take care of the fact that they need to be added to other data that already exist. So there is some work to do, but I think the community is becoming aware of this.
I can jump in. I mean, I echo a lot of what Cecilia said, and I think it was Miguel who had mentioned that economics might be like a very data-rich field. I think that's maybe true, but it's certainly not at the scale of like Google-sized data sets, and in particular in where I work, which is like applied microeconomics, and in particular a focus on like development. There are no standardized data sets, and it's a big problem. I mean, Cecilia mentioned how like different labs conduct the same experiments, but generate under slightly different conditions. Now imagine you're designing like education policy in Nigeria and you want to compare it to education policy in Malawi, and it's just really hard to know what the differences are between those contexts, even if the data are available. And I agree with Cecilia that there is a big push towards transparency in open science and economics. You know, overdue, but I think the field is moving in that direction. But it's not clear how to synthesize those data sets into like a single training data set or something like that. I think one other area that I'm particularly optimistic about, though, is there is a bunch of work in machine learning methods through reinforcement learning, through online learning, active learning, or in statistics, it's often called adaptive sampling. But to think about a technical problem of when it's very costly to obtain data or to obtain labels for data, what is, an optimal or efficient algorithm for determining where to collect those labels. And so I think this is something where even if existing data sets are small, if we have very smart ways to think about where to gather data and how, that can allow us to, get the most bang for our buck. Because at some fundamental level, if survey data is the foundation of development economics, we're not going to get around that with machine learning. It's very costly to send people to houses in rural Africa and have them conduct full day interviews to collect training data. But if we can be a little bit more judicious about that, that could go a long way.
Yeah, I don't have much to add. I think the challenges are similar across the board on this one, right? Some fields have more data, other fields don't have as much. Some fields are a little bit ahead than others. I would say in mechanics, there's a big need for sharing data and standardizing the different sources of data and how to curate it and so on. I know that Emma is already doing some nice work on that front there, and we need these sort of initiatives. And then what Joshua said exactly. So if we have data scarce problems, cases that we really cannot get around it, things like online learning, like Bayesian optimization or other methods where you can actually adaptively sample and really try to, or hopefully estimate where the right sample makes a big difference in the learning process. That was also something that we presented on in my talk at the end with a nanomechanical resonator. These are the sort of things that we can do. So there's lots to do, really. You can do data scarce things, you can do data intensive things as well. The challenges are quite different, but there's an opportunity for pretty much anyone that wants to jump on this. So there's really lots to do.
Yeah, just to round out the discussion, in my field, there's certainly a ton of data. We have spacecraft going around the Earth, collecting tons of data around other planets, and we have a ton of data. But the interesting part is if you just take like one little step over from my field into an adjacent field of solar physics, we have too much data, I think. We have, like in my home country of South Africa, there's a new project called the Square Kilometer Array. It's basically a bunch of antennas, and between them the effective aperture. It's split between South Africa and Australia, and between them they're going to have a square kilometer of effective aperture imaging the sun, and they threaten us with replicating the entire internet's worth of data in the first week of operations. They literally have to build a warehouse right there to store all this gigantic amount of data. And it just kind of makes my heart palpitate a little bit, and I just kind of worry about machine learning. Machine learning chokes when you give it so much data too. It's just like a computer that it's just gonna die if you give it that much data. But it's our best hope of processing that quantity of data. Now, with that said, I'm gonna jump off something Miguel said, is that not all the data is that useful. Like 99% of the data is just going to do what we think it's going to do, and it's not going to tell us anything new. And so the question becomes, then you're just looking for a very imbalanced little number of points to kind of squeeze out something that is going to give you all the information. And I think this is probably something that translates to many fields, is a very small number of points in a very particular point in your phase space is going to tell you something that's revolutionary and probably going to win the Nobel Prize, right? For figuring out how the corona heats or something. And so the challenge to machine learners is not how you process the gajillions of bytes of data that's going to come down, but how do you quickly run through all the data that's not informative, hone in on the stuff that is very, very informative, and make full use out of that. It's a very subtle problem.
Yeah. So if we're ready to move on to the next question, it's very much related, and I think I'm actually going to reformulate it a little bit on the fly based on the responses here. I'm curious, is the efficacy of new methods in your field evaluated? Often, in computer science applications, particularly, I'm thinking of computer vision, there are a bunch of benchmark data sets. And if a new method does well on one of those benchmark data sets, we know that it's potentially worth something. Is there an equivalent or something similar in your fields that you look to? And maybe we'll do the reverse order again.
Okay, so I guess that's me. There's no like standard community-wide data set. There is a kind of a very common problem that people all try out, including all my students. You take the solar wind parameters and you try and predict what geomagnetic indices are going to do, and it seems to be like a very popular problem to do because the data is all available and it's in ASCII and it's like one big gigantic table that you can just load in your computer and you can play with algorithms. So people do that. In terms of actual benchmark data sets, some people are trying to organize it, but not really. But what is happening is it's sort of like a chaotic swarm, if you can imagine little particles, and people vote with their feet. And so when there's something interesting and there is some value being recognized, kind of the swarm all migrates to the interesting problem, to the interesting data set, and people just start playing and trying it out. And in a way, I think it's not a bad thing. It's organic, and it allows for the system to just kind of evolve dynamically, just according to interest and perceived promise. I think to some degree that's maybe happening in other fields too, but maybe others are better organized than we are.
I guess I'm next in that order. I don't have a lot to say. I think in economics, I am not aware of anything even remotely like ImageNet of these sort of benchmark data sets. I think I could point to a couple of small examples, right? Like there are some labeled data sets and competitions that have been put out by social scientists. Like there's a Fragile Families Challenge that Matt Salganit's group at Princeton launched to see if people could basically predict outcomes for people like over time. Which my understanding of the postmortem was that even the best machine learning researchers were remarkably unable to generate accurate predictions. There's also been something similar in these like predicting poverty from satellite imagery, but these are very, very small scale. I think when you speak about what are the standards that the field typically uses, I think at least in applied microeconomics, randomized control trials have really become a de facto standard for evaluating the effect of different policies. And so one thing you see is, at least in this machine learning meets econometrics field, where people are trying to use machine learning to derive causal estimates, is you'll see people compare the simulated outcomes using machine learning to the actual outcomes that were measured using a randomized control trial. So it's far short of like a benchmark data set, but at least it's sort of like a convergence on some sort of methods for using data to validate machine learning models. But I think there's it's an area where there's a lot more that needs to be done, definitely.
Yeah, so in terms of benchmarks, I already mentioned in my field, there's not a lot going on at the moment, but hopefully that will change. But I would like to then speak about that case where you actually are reviewing papers or seeing it other person's work, and you actually have a lot of difficulty, let's say, to even understand the quality of the model, because we see, at least I feel that there's a big difficulty when you're evaluating machine learning papers, especially the applied ones. I think, again, the computer science community has benchmarks, and they've been doing this for a while. So most of them, at least in good conferences, they're a bit more organized, and they have these benchmarks and so on, and validated a little bit more extensively. But in the applied fields that I'm in, you don't see that. So basically there's a data set that is created by themselves. Oftentimes it's not even shared, that, unless you go to high impact journals like Nature, that, for example, requires you to share that with the reviewers at least. And then, you have these non-parametric models full of parameters that we cannot probe. And it's very difficult to actually know, is this actually a predictive model, or did something happen like Jacobs mentioned before, where a simple linear regression model would just do fine. So what I typically ask, at least in my field, is when you see a prediction or key prediction in the paper, the first thing I ask is, show me a few points, 10, 20 points, 5 points, depending on the data set, close to it on the training set. How close are you actually from getting there? And it's surprising how that actually is a huge difficulty to some people to actually explain. And they don't have a model that is that predictive or that doesn't generalize so well. Because in fact, a lookup table would be almost as good in such a circumstance, right? So the lack of benchmarks can be a big issue and a big hurdle to move the field forward and to actually avoid having the hype of machine learning kind of be a bad effect later on.
Yeah. Oh yeah, please, Cecilia.
In my field, there are some, we start to see some benchmarks, but again, for what I call the easy cases, like predicting energy of molecules from the coordinates of the atoms. There are several data sets that have been created and proposed as benchmark, like QM7, QM9 are famous data sets that everybody uses to measure the performance of their model. Basically, these are synthetic data sets. They are created by, I don't know, like quantum mechanical calculation, and are considered the truth, although they're not, they are still a model, but it's a very expensive model, and you want a machine learning model to reproduce this data very efficiently. And this is what has been used. But I think we need to have real data, like experimental data, true data to compare with. And this has not been done yet.
Something's been hinted at a little bit is how some machine learning models sort of lack interpretability and ability to map certain variables back to actual physical things or something we actually know of. Has this been a problem in your field in particular? And what are the sort of steps that have been taken to address, mapping what comes out of a machine learning model to actual physical known quantities?
I can jump in, but I think I've said this a bunch of times, but causal inference is really at the heart of machine learning. Sorry, at the heart of economics. And at some fundamental level, it's hard to have causal inference without interpretable models. And so I think that tension has really initially turned a lot of economists off from machine learning. So I mean, how do economists deal with this? Well, one answer is to use Lasso instead of more sophisticated machine learning models, because like most applied econ, most economics papers that have any empirical component at some level have like a linear regression as the workhorse model. And so the issue of variable selection is real. And so you see a lot of recent papers that are relying on Lasso. I mean, I'm saying that partly facetiously, but it's actually true that where you see the machine learning infiltrating economics is really like at the periphery, sort of where economists are using machine learning models to really like tackle a very specific aspect of a larger problem, right? Like I mentioned in passing this notion of machine learning for heterogeneous treatment effects, but I think it's a good concrete example where very often you have some sort of policy intervention and you're interested in understanding on average whether the population benefits from the policy, but B, then understanding if there are specific subgroups of the population that benefit more than others. And so traditionally economists would use linear models to model these sort of questions. And they use theory to determine, all right, what are the subgroups of interest? Do we care about men and women? Do we care about high income versus low income? And they enumerate a finite set of these subgroups and then test each one by one, and then worry about p-hacking and multiple testing. But now you see sort of a paradigm emerging where people are using machine learning models to let the data tell you amongst which subgroups of all the possible subgroups you see, statistically large treatment effects, different from the average treatment effect. So, that's like one very specific example, but it is fundamentally a machine learning based analysis that is now being sort of lemmaed into a lot of empirical papers in a way that even just a few years ago you didn't see at all. And so, I think it's sort of baby steps. Once people get comfortable with that, then it'll start to become a little bit more central in the analysis.
Yeah, I think in my field, the way at least I approached it was I started by dealing with what's called constitutive models. Basically, the material behavior is the result in mechanics, is the result of millions of different elements that come together to produce that macroscopic behavior. And the truth to the matter is that most of these models are already empirical. They are called phenomenological. So they model phenomena, but they are not physically based. And to me, I think that was the most interesting entry point for the literature to kind of motivate the community, because you have a very simple argument. If your model is not physical already, you cannot criticize the use of a machine learning model that is modeling better and faster. And there's another catch. Unlike many other fields, constitutive modeling in materials involves usually are iterative models, so you don't have the full solution. It's not closed form. So when you deform a material, you find the stresses or the forces per unit area iteratively. So you have to then come back to the strains and then compute, is this stress consistent or not? If it's not, then you iterate again, which means that in a material to actually get this behavior iteratively, you have to solve, use Newton-Raphson schemes or whatever, which take a long time to converge. So in my view, when I was first analyzing this, you don't have the criticism of the empiricism, and you have a much more accurate model and incredibly faster. So it's one of those fields that, it's undeniable. That's why now it's becoming so popular as well. That is very useful. But this is not true for every mechanics problem, of course. There are mechanics problems where there is very good theory and it's related to lower scale physics, for example, that can be derived from Cecilia's work. And in that case, then it becomes a little bit different. Maybe those multi-fidelity techniques, or maybe you reserve machine learning to the parts that you don't know, and you handshake it with these kind of models. And there's another thing that also Jacob mentioned before. We also have a little work on that, where you can use machine learning to derive new physics equations that actually extrapolate well outside the bounds of the training domains as well. So, which is a very exciting field. And Hod Lipson, I think, was the pioneer of this at Columbia now. He was at Cornell at the time. So basically, you kind of derive these physics laws from machine learning algorithms, getting that interpretability. So it really is dependent on how you look into it, but there's solutions for pretty much every perspective, I think.
Yeah, I think I'll use Miguel's excellent answer as a jumping off point. And so, yeah, the Schmidt and Lipson was actually the paper that got me really interested in machine learning. It's just kind of a classic paper that takes simple systems like springs and pendulums and just looks at the data and writes down Hamiltonians and Lagrangians, and so you just derive your equations of motion. It's like magic. But let me go back to the main question. In my view, there are two related problems. One is much more serious than the other. The first problem is the interpretability of black box models. That is actually not the serious problem. There are black box models, but there are approaches like layer-wise relevance propagation, there are heat maps. There are things you can do to kind of tell you how your inputs affect the output, or how they interact to affect the output. So there's the interpretability of the models themselves. The second problem, and the much more serious problem, is the interpretation. And this is on the scientists. I mean, whatever model you have, I mean, even if you go to the Large Hadron Collider and you squeeze out tons of data, well, that data has a problem with interpretability too, right? I mean, we have to do the work to squeeze out the knowledge. And it's the same thing with machine learning. We can derive a model, but then it's on the scientist, it's on the user to interpret it, to actually go back to the physics, to the understanding, and to kind of probe your model and to say, what is actually being captured in this model about my system? That is a much harder and much more subtle problem. But, and that's kind of like a sociological problem, right? It's like, it's on us, and it requires depth, it requires finesse. It requires a new way of working with a machine learning model to extract fundamental physics out of it.
I agree completely with what Jacob had said, and in my field, there is now people are starting to shift from just predicting the outcome to try to dissect the model to see what's inside. For instance, instead of just a neural network, people are trying to build what they call representations of atoms and molecules, meaning to simplify the neural network or the machine learning model as much as possible and put the knowledge into the features. So the input. If you prepare the input, if you transform the input with a lot of physical information, then you can simplify the model. And the goal would be to make it very, very simple and put all the information into the input. Then is a way, is like reverse engineering the network, and you can understand what are the ingredients that make it work.
Yeah, thank you. I think we have time for one more question. I don't know if there's a preference between the two. Maybe I'll just go ahead and ask the one that I'm kind of most curious about. So what do experts in your field bring to the table that people with expertise in machine learning, but no expertise in your discipline may lack? And then sort of following on that, is there a push to make data-driven problems in your field more accessible to others? Why or why not? I think Josh touched on this a failure of this before with making data sets and the social science accessible and not necessarily seeing any beneficial outcomes from that. I'd be curious if people have thought about this.
Is it me? Are we going in reverse order?
Yeah, please.
I'll just jump in. Okay, what do experts bring to the table that machine learning, just machine learning expertise? Well, I think that's a pretty easy one. When we set, kind of our machine learning heavy colleagues on our problems, they basically kind of rediscover everything we already know. And they have no sense of which problems are important and valuable, what questions we actually have in the back of our minds. And they kind of, they just don't have a sense of the relative importance of the different questions and problems that we're looking at. And so it's hard to be a machine learner in a specific discipline because you have to know both. You have to know your discipline very well, what problems are important, what work's being done, what questions exist, and what kind of paradigms you're trying to discern between. That's the kind of the domain specialist's job. And then you have to know about the machine learning side and what the limitations are and what it brings to bear on your problem. Is there a push to make data-driven problems more accessible to others? Yeah, to some degree. Although people are busy and everyone is doing their own science and writing their own papers and proposals. And so to just kind of devote a huge amount of effort into creating tools and open data sets, people wouldn't do that kind of whole scale on a volunteer basis. And there's no real dedicated funding, right, for people to say, okay, you guys go off. And even if there were, what is the benefit to a fundamental physical scientist to do that when you don't get essentially publications, citations, the metrics that scientists generally care about? And so maybe that's a gap. I mean, maybe that's a paradigm shift that's community-wide that needs to be looked at, and to say, how do you give scientists some value back for doing this kind of work?
Yeah, I might not have much to add here. I think there are some very good examples out there where having domain knowledge made a huge difference. The one that comes to mind to me is Max Velling in Amsterdam, where he basically did gauge invariance for neural networks. And basically, you know, the material scientists jumped on that immediately, right? Because you have the molecules rotate, and you want it to be the learning to be invariant to this rotation, which is not giving you much. And that led to a huge jump in terms of the quality of the models. And that, of course, was created with a different thing in mind. I think it was for imaging of 3D organs or something like that. But, you know, the experts in the field realize that there's a need for this in their particular problem. And I think, in fact, nowadays, because this is becoming so important for so many people, in my view, that's what distinguishes the leaders from everyone else. Those are the people that actually look at the field and see, okay, you know, in my problem, I have these key aspects that another person from that field doesn't know. And if that same person, if that person does not know, then it cannot encode that knowledge into the machine learning algorithm. Therefore, their learning ability and that predictive ability has to be worse than the domain knowledge experts, right? So I think that's the dynamics, and as of now, it makes a huge difference to know enough about the field. I think, at least for a large class of problems. Maybe in the future, when you have artificial general intelligence, maybe we'll be all out of job, but I think that's a bit far from now.
I mean, I will mostly just echo what Jacob and Miguel have said, that I think, I mean, maybe it just seems particularly so to me because I live in that space, but it seems to be the case that particularly for social sciences, when you're trying to understand human behavior, it's like, it's really important to understand the substantive questions that you're asking. And so I think there's a lot of very highly publicized missteps when pure machine learning researchers or applications are deployed on social systems, and then the predictions just either go haywire or just like encode horrible biases that existed in the data that were available to the scientists, but that did not reflect larger attributes of the system, because the data just only reflected one subset. So I think it's critical that there's like this domain understanding is involved when you're applying machine learning onto social science problems. I think where you see more action and investment is now in sort of the training of social sciences. So like most econ grad students will now take courses in machine learning in the course of their graduate education in a way that didn't happen 5 or 10 years ago. And so I think it's probably going to be more the case that that it'll be economists that endogenize this expertise and start to use it themselves, rather than like an outside pure computer scientist says, hey, I'm going to work on this data set from a social system and like derive some tremendous insight that has eluded us until now.
I agree completely. And but I think there is an interest in the machine learning community to learn about the domain field, because they understand that the range of applicability of their method can be potentially much larger rather than just images. For instance, they invited me as an invited speaker to ICML, that is International Conference on Machine Learning, to talk about the machine learning AI in science, because they want to learn. This is a conference mainly for computer science, for machine learners. They want to learn what are the potentials in the field. And but I think there is the danger a little bit of just putting this on others, saying, oh, they have to learn our field. I think it's also a little bit on us to learn the tools and decide what can be used or not, because we cannot just blame the computer scientists are not understanding what we're doing. We also need to understand what they're doing and what is possible or not possible as an algorithm.
Yeah. Thank you so much, everybody. It's 12:01 exactly in Eastern time, so I think perhaps we'll wrap it up. But thank you, everybody, for doing this. That was really insightful conversation, and thank you, Allison, for co-hosting. I don't know if you have any other final words. If not, just thank you for doing this, everybody.
There's no further questions from the audience. Again, thank everyone for their time. And you'll be able to find the recording of this on the YouTube channel if you have to go back and review any content. So.
Yes. Yeah. Thank you for mentioning that. All right. Goodbye, everybody.